Okay, so welcome to all of you. Today we will see what do we mean by greatest common divisor, that is GCD. So in Marathi it is called MSAVI, right? Mahत्तम साधारण विभाज्य. Okay, so in Marathi it is called GCD. So before the GCD we will see what do we mean by common divisor. Okay, so suppose we have two integers a and b. Okay, so not both 0. So the integer d is said to be common divisor of a and b if d divides both. That means what? D is the divisor of a and b. That means d divides a, d divides b. Okay. So now we'll see what do we mean by greatest common divisor. Okay. So this is the actual definition of the greatest common divisor. Okay. So you have seen how to find the greatest common divisor. Okay. So you have not seen the definition of the greatest common divisor before that. Okay. So now see, we will define the greatest common divisor properly. Okay. So let a and b be the given integers, not both 0. Okay. So that means a and b are any two integers such way that one of them is not 0. Okay. Then the greatest common divisor of a and b is denoted by GC. This is read as GCD of AB or simply in the open bracket AB. So this is just like an open interval AB. But now this is what in algebra. So this is AB is not a point. Okay. So it is what? It is what? GCD of AB. Right. So in algebra, we have to consider this meaning as open interval AB, meaning of this open interval AB as GCD of AB everywhere. Okay. So now, so is a positive integer d. That means GCD of AB is denoted by this, and this is a positive integer d such way that means this satisfies the condition. It divides both. That means it is common divisor of both A and B. Then any common C divides A, C divides B. Then C also divides D. That means what? Any common divisor of A and B also divides D. Okay? So when we say that D is a GCD, if D divides A, D divides B. And any common divisor of A and B also divides D. Right? So this is the definition of the GCD. So we have some points: A in integer, then A is not equal to 0. Then GCD of A0 is mod A. GCD of A1 is equal to 1. GCD of both A, the same number, is the magnitude of itself. That means what? GCD of minus 27 and 27 is plus 27 because GCD is always positive. Okay. Now GCD of AB is same as GCD of minus A. One of them is minus whatever this. GCD of AB is same as GCD of minus A. B. GCD of A minus B minus A minus B. All GCDs are same now, right? One of them is minus, doesn't matter, or both are the minus, doesn't matter, right? GCD is always positive. Okay. So now if C divides A, C divides B, that means C is the common divisor of A and B. It is also divides the GCD. So common divisor also divides GCD. So this we have seen in the definition also. Okay, and we have seen in the note also. So these three notes are also important. This definition is also very important now here. So remember this is what? A and B are any two integers, not both 0. Then GCD is denoted by this AB or this, right, which is a positive integer D such way that you are satisfied that D divides A, D divides B. You see any common divisor of A and B also divides D. These two conditions are very important, right? So GCD is what? GCD what? It is first, it should be the common divisor. First condition is what? It should be the common divisor. And second condition was any common divisor also divides this. So for example, if you consider this 20 and 40, and what is the GCD of 20 and 40? See, 2 is the common divisor. 2 is the common divisor of 20 because 2 divides 20, 2 divides. So that means what? 20 is the multiple of 2, 40 is multiple of 2. Okay. So now here what? 4 is also common divisor. Okay. 5 is also common divisor. 10 is also common divisor. 20 is also common divisor. Okay. Now see. So GCD is what? GCD, you know that GCD is what? 20. GCD of 20 and 40 is 20. Now see here. These are the common divisors. These are the common divisors of 20. Right? See, this 20 is the common divisor of 20 divided 20, 20 divided 40. Right? So that means 20 is the common divisor. Okay. Now 2, 4, 5, 10 are common divisors. They also divide 20 now. They also divide 20. Now see here. So 10 is not a GCD because what? They are the common divisor. 2, 4, 5 are the common divisor. But they do not divide 10. That means what? 10 is not a. That means what here? 4 do not divide 10. Right? 2 and 5 divide 10. No problem. But 4 do not divide 10. That means 10 is not a GCD. Right? So 20 is the GCD. We all these are the common divisors. Also divide this. Okay. So that means what we are finding the GCD of two numbers. We are finding the GCD, that means greatest common divisor of two numbers. That means what we are finding. So that means we are finding a greatest number such way that that number is divisible. That number divides both. That number divides both. This is the greatest number. This is the greatest number. This is the greatest number which divides both the numbers, right? So 20 is the greatest which divides 20 and 14, right? So now we'll see some some theorems on the GCD. So one theorem is very important here. So theorem. If A and B are any two integers, not both zero, this is the definition actually, not both zero, then there exists unique, then there exists a unique positive GCD of A and B, which can be expressed in the form D is equal to A x naught plus B y naught, x naught y naught belongs to Z. Okay, so we prove this one. Proof. So that means what is the theorem tells you? A and B are any two integers, they are given. Okay, so not both zero. Only I have A and B. We don't have now D now. We don't have D. So what do I have to prove? GCD of A and B is exist. GCD of A and B is exist, right? So, and which is unique, and it also can be expressed as A x naught plus B y naught. That means there exist two integers x and y such that whatever your GCD is nothing but A x naught plus B x naught. That means what GCD can be expressed in the form linear combination of the given integers, right? So what we have to prove? We have to prove that for any two integers we have the positive GCD, and that GCD is unique. Also that GCD is expressed as a linear combination of A and B. This we want to prove. Okay, so proof. Consider the set S is equal to AX plus BY, XY belongs to Z, AX plus BY strictly greater than 0. Okay, so let A and B are, okay, we have actually, since we write since. We have to prove this one. Since A and B are integers, not both zero. Okay, so therefore A square plus B square, this is always greater than or equal to 0, strictly greater than 0, A square. So this is therefore what? This is what? A into A plus B into B, this is greater than 0. Right? Now this is of the form Ax plus By. This is what? Greater than 0. So that means what? This is what? A square plus B square belongs to S. Right? This is the element of S. So we have only A and B. With the help of A and B, what we have? We have formed this set and we have shown that S has at least one element. So that means what? Whatever this may be, your A square plus B square is always the element of S. That means what? S has at least one element. So if a set has at least one element, we are saying that that set is not empty. So therefore S is non-empty subset of. Now see here, this ax plus by is greater than 0. Ax plus by is greater than 0. That means a is integer, b is integer, x and y are integer. That means ax plus by is the integer and that is greater than 0. That means it is a non-empty subset of the set of the natural number. So therefore, so we know that, so if any subset of n positive integer, that means what, union 0 is also there, right? So any non-empty subset of natural union the similar than 0, that means what, the any non-empty subset of the positive integers, any non-empty subset of the positive integers has a least element. So we have seen that by well ordering principle. Okay, so therefore by well ordering principle, S has least element. Least means smallest element. Say D. Okay. So let D be the positive integer. So that means what, here D belongs to S. That means what? So therefore D belongs to S. And we know that elements of D is always of the form Ax plus by. So therefore D is equal to a x naught plus b, y naught, x naught, y naught belongs to Z. Okay, so I can say this. Now what is our aim now? So what we want to prove? For any two integers we have the GCD and that GCD is unique, that we have to prove. Okay, so we have, and also we have to prove that can be expressed in the form ax naught plus by naught. Okay, so now if you prove D is the GCD and it is unique, then our problem is over. So if D is GCD, then see GCD is expressed as in the form x naught plus by naught. So that part is over. So that means when your theorem is over, so if you prove D is the GCD and it is a unique, then our theorem, the proof of the theorem will be over. So first we will prove D is the GCD. So you have to prove D is the GCD. That means what we have to prove? We have to prove that D divides A and D divides B. So first we have to prove D divides A, then we will prove D divides B. What is the definition of the GCD? Definition of GCD what? D divides A, D divides B, right? And the second condition what? Any common divisors of A and B, it divides GCD. These two parts we have to prove. Okay, so first we will prove D divides A, right? So that means what? A is the divisible by D, B is the divisible by D. That we will prove. That means what we will prove? A is equal to D times some integer. Suppose Q1. This you have to prove. A is equal to D Q1. Okay. So what we will do? We will apply. So aim. We want to prove D is GCD of A and B. This we have to prove. Okay. So if you prove this, almost the theorem is over. Only I have to prove the uniqueness then. Okay. So what we will do? What we will prove? D divides A. So what we will do? We will apply the division algorithm for A and B. Applying division algorithm for A and D. So now A is the biggest number. So A is equal to DQ plus R. Now D is positive. D is what? Positive. So just we have to write only 0 less than R less than simply this is what? No D. No need to write the mod D now here because D is already positive. So what we have to prove? Our aim is what? To prove that R is equal to 0. So what is that? We want to prove R is equal to 0. Remainder is 0. What we have to prove? D divides A. That means what? D divides A. That means A is equal to DQ. We have to prove. That means we have to prove that R is equal to 0. Okay. So if not, that means suppose you want to prove R is 0. So let if possible r greater than 0. That means what? Suppose r is equal to 0 is not possible. Okay, so we consider r is greater than 0. Then what happen? That means what? What we are assuming that r not equal to 0. Our assumption is what? R not equal to 0. That means what? Make it possible r greater than 0. Okay, so then r is equal to what? A minus dq. A minus dq. So now we will put the value of d now here. So a minus, your d is what? Ax naught plus by naught q. Right? This is your value of d. I will put the value of d here. Now we will simplify. We will take a common and b common here. So if you take a common, you have to multiply by this q. Then this is 1 minus x naught q minus, I will write here plus. I will write here plus. So I will write here b. Then this is what? Minus y naught q. Minus y naught q. Now see, this is r. And this is what? R is greater than 0. This is r, because r is what? R is what? R greater than 0. Right? So this is greater than 0. Now r is of the form ax plus by. R is of the form ax plus by. And any number of the form ax plus by is the element of S. What is your S? S is what? Ax plus by. Xy belongs to Z. And this is what? Ax plus by greater than 0. Right? This is your S. Now see, this r is of the form x plus by. That means what? This implies that r belongs to S. R belongs to S. Right? And what is your r? R is less than d. R is less than d. R is less than d. So your r is this d. Right? So either r is what? Positive or equal to 0. R may be positive or may be greater than, may be equal to 0. And so r is less than d. This is correct. Because what? You are applying the division algorithm. So r is less than d. This is correct. Now what is this? R is the element of S and r is the what? Smaller than d. So what is our d? What is our d? D is the smallest element of S. That means what? No number less than d is the element of S. So now your r, this is number, r is less than d. R is less than d. So and d is the smallest element. D is the smallest element. Smallest element. D is the smallest element. That means no number less than d. No number less than d is the element of S. So here what? R is the number which is less than d and it is a member of S. Is it possible? No, this is not possible because only d is the positive. That means what? If your the smallest element is 4, so that means what? We have proved that 2 belongs to S. Is it possible? So S has the smallest element which is 4. That means no number less than 4 is the element of S here. So what we have? If 2, is it possible 2 belongs to S? No, this is not possible because the smallest element of S is 4 here. Right? Same thing here. What? The smallest element of D is 4. D is the smallest element of S is D. And what we get? R is the element of S, which is the smallest of the D, which is the smaller than D. Right? So this is not possible. This is not. This is contradiction to the fact that D is the smallest element. D is the smallest element of S. So we must have. So why we get this contradiction? Because our supposition is wrong. What is our supposition? R is not equal to 0 is our supposition. That means what? R greater than 0. That means what here? R not equal to 0 is our supposition. Due to wrong supposition, we get the wrong answer. That means what? R must be 0. So therefore we must have R is equal to 0. So R is equal to 0. So R is equal to 0 means what? So therefore A is equal to dq. Therefore A is equal to dq, and therefore D divides A. We call this as capital A. So we have proved that D divides A. Okay. Similarly, we can apply the division algorithm for B and D, and same thing here. Play the same role for write all the things for B here. So no need to write all the things. So just we will write similarly. Similarly, we can prove D divide B. Okay, so we call this as B. So from A and B, D divide A, D divide B. So we call this as 1. So we have proved that D divides both. So now what we have to prove? Any common divisor also divides A. Okay, so let C divides A and C divides B. So what does this implies? A is equal to C times we'll say x1 and B is equal to C times x2. Okay, x1 belongs to Z, right? By definition of this, what we have to prove? C divide D. We have to prove C divide D. Okay, so what we have? A is equal to this. So we have D is equal to A x naught plus B y naught. What is your A? C x1. So C x1 x naught. What is your B? C x2 y naught. So therefore D is equal to C into x1 x naught plus x2 y naught, right? So x1 x2 x naught y naught all are integer. Product of the two integer is integer, sum of two integer is integer. So this implies that C divides D, right? Because D is equal to C times some integer, that means C divides D. So thus C divides A, C divides B implies that C divides D. We call this as 2. So what we have proved? D divide A, D divide B. Then any common divisor also divide D. So from 1 and 2, from 1 and 2, D is GCD of A and B. From 1 and 2, D is the GCD of D is the GCD of A and B. Okay. Now uniqueness. Let if possible. Okay. Let if possible. D is equal to GCD of AB and D dash is also GCD of A and B. Okay. So D divides A 1. Okay, we'll say 1. Okay, D divides A, D divides B, and D dash is a GCD of A and B. Now see here, D is the GCD of A and B, D dash is also. So what we'll say? So first we will assume that D divides A, D divides B, because D is GCD. They divide both, and D dash is what? Now we are assuming that D dash is GCD, right? And D is the common divisor of A and B. So by definition, so what does this implies? D divide D dash. Now secondly, what we will assume that D dash divide A, D dash divide B, and we will assume that D is GCD now. So what we will assume that D dash is the common divisor and D is GCD. What does this imply? D dash divide D. Any common divisor divides GCD. Okay. So therefore D divides D dash and D dash divides D. That means they are the divisor of each other. That means what? So this implies that D is same as plus or minus D dash. But both D and D dash are positive. Both D and D dash are positive. So therefore D is equal to D dash. Okay. So that means what? GCD is a common. So this is a very nice theorem, and this is a very nice proof of the GCD, right? This is very important theorem. So you should remember this along with the proof. Okay. So independently you should write the not the statement of the theorem, but the proof of the theorem. You should independently write the proof of this theorem. Okay. So now we'll take some examples on the GCD. So we'll apply the application of the definition of the GCD we'll see, and this theorem also. Okay. Okay. So now we'll say first co-prime. Co-prime numbers. Co-prime numbers. Okay. The two integers definition हो जाएगा. Two integers a and b not both zero are called co-prime numbers if GCD of AB is equal to 1. If GCD of AB. Okay. So then A and B are also called as relatively prime integers. That means A and B are relatively prime integers if GCD of AB is equal to 1. So if their GCD is 1, so that means, or for example 2, 5. That means 2 and 5 are the GCD. 2 and 5 are the relatively prime or co-prime. So -2, -7 also. This is also 1. GCD 1. GCD is always positive. Okay. So this GCD, don't write this as -1. Okay. So that means what here? So I hope that you understand. So if their GCD is 1, then that numbers are relatively prime or the numbers are co-prime. Okay. So you can take a even order like this one. 25 and 30. Note that this is even and this is. These are not. GCD is not 1 here. GCD is 5. Okay. So that means they are not relatively prime. Note that. And because what? 5 is the common divisor. That means what? The common divisor, only 1 is the common divisor. Right? Only 1 is common divisor. Then they are called relatively prime. Okay. So we take a theorem or problem example. Okay. Let A and B belongs to Z. Let A and B belongs to Z. Not both zero. Then A and B are relatively prime if and only if there exists XY belongs to Z such that 1 is equal to AX plus BY. 1 is equal to AX plus BY. We have to prove this one. Proof or solution. Okay. So if and only, that means there are in 2 parts. Okay. So we take part 1. Okay. So what do I have to assume that A and B are relatively prime? Part 1. Assume that A and B are relatively prime. So therefore what? They are relatively prime means their GCD is 1. Okay. What do I have to prove? There exists 2 integers x and y such that GCD is 1. Okay. So GCD is 1. So therefore there exists xy belongs to Z such that 1 is equal to AX plus BY. Okay. So this is by the previous theorem. Okay. So the first part is over now. Okay. Now second part 1. Okay. Part 2. Part second. So what I have to assume that, so A and B are the 2 integers such that so assume that 1 is equal to AX plus BY. This will assume that. And what we have to prove? A and B are relatively prime. Okay. So let AB is equal to D. So what we have to prove? So D is 1. This we have to prove. Okay. So what does this implies? This implies that D divides A D divide B. Right? What does this implies? D divide AX, D divide BX. Right? So D is the common divisor of A and B. This is the definition. So any this is D divide say D divide B. This implies that D divide AX plus BY. We have proved that if D divide A, D divide B, then D divide its sum also. Right? But AX plus BY is what? AX plus BY. So AX plus BY is 1 now. So D divides 1. What are the common divisors? What are the divisors of 1? Only plus or minus 1 are the divisors of 1. So what does this imply? What does it imply? D is equal to plus or minus 1. But D is positive. But this implies that D is equal to 1 since D greater than 0. So D is equal to 1. So what do I assume that D is GCD of A and B? What do I prove that? D is equal to 1. So therefore GCD of AB is equal to 1. This implies that A and B are relatively prime. Relatively prime. So problem no 4. Okay. So if there is if and only, so for in the part 1, assume the left of the if and only and prove the right of this one. In the second part, assume the right part of the if and only and prove the left part of the if and only. Okay. So the same thing we did here. Okay. Now we take, this is also just like as a theorem. Now here what in algebra all the problems are just theoretical problems. Okay. Now we'll take the next one. Okay, so we'll take a note now. If AX plus BY is equal to 1, then GCD of AB is equal to 1 from this and 1 from this one. So we have taken A, so I will take AY now here. With A I have taken B, with A I have taken B. Now I have with the X now. X I have taken B with X now. So then what? X, Y. So this is 1. Right? So that means what? If this linear combination is 1, then take 1 from the first term and second from the second term, and GCD is always 1. GCD of that element is always 1. So that means what? Whenever you have this AM plus NY is equal to 1, then what? GCD of AY, you can write this GCD of AY is 1. Because 1 from this one and 1 from this one, so then GCD is always 1. If you have the linear combination is 1, then take whatever this you want, take the first one term, one element from the first term and one element from. So similarly what here? AXY plus BMN is 1. Then also this is whole, right? AB is equal to 1. This also this. AM is equal to 1 also. GCD of AM is equal to 1 also. Take 1 from this and take 1 from the second term. So that GCD is always 1. Note that. Okay. So this note is very important here. Always remember this one. We'll use it in some problem. Okay. We'll use this thing. So remember this note. So if this example, next example, whatever the number, right? If GCD of AB, is D, then GCD of A upon D, B upon D is 1. Is 1. Okay. So proof or solution. Okay. Now we'll take solution. Okay. Given that AB is equal to D. Okay. So this implies that first we will apply the definition. D is the common divisor of A and B. So D divides A, D divides B. We will apply the definition. Okay. A is equal to DQ1, B is equal to DQ2. Okay. Where Q1, Q2 are the element of Z. Okay. Also we have right. So D is the GCD of AB. That means there exist two integers X and Y such that D is the linear combination of A and B. So also we have D is equal to AX plus BY. X, Y belongs to Z. This is also by theorem. We have proved this. GCD is always expressed as a linear combination of A and B. Right. Now what is this then? This is what D is equal to, so here what, we'll divide by 1 now. We'll divide by 1. We'll divide by D because GCD is always positive. That means it is not 0. I divide this. This is what? A Q X, A D, A upon D. Then B upon D Y. So A upon D is what? Q1 now. Right? So this is what? Q1X. So B upon D is Q2Y. Okay. Now what is this? This is what here. So Q1, this implies that. See, Q1X plus Q2Y is equal to 1. That means what? GCD of Q1, Q2 is 1. GCD of Q1. See, this linear combination is 1. And just we have seen the previously, 1 from the first term and second from the second term, that GCD is always 1. Okay. So what is your Q1? Q1 is A upon D, B upon D. So this is 1. Okay. So now here Q1 and Q2 are integer. So what I have to show actually, A upon D is the integer. A upon D is the integer. Because division of two integers need not be integer. This may be integer. Okay. So why I written this Q1 and Q2? So because I want to show that. So I want to show that this A upon D is the integer. So therefore I have written this one. Actually directly I can write here also A upon D is right. So why I have written this? I want to show this A upon D is the integer. That's why I have written this. Actually directly from this one you can write this one. Right? Okay. So now directly you cannot write this one because the division of any two integer is not integer. So that's why I write this. Right? So now our theorem is over now here, or our problem is over here. Okay. So we'll take the next one. So just with the help of the definition of divisibility and the GCD, we have proved the theorem. We have proved proving these problems also. Okay. So now we'll take the next one. If A divides C, and B divides C, so A divides C, B divides C. That means what? A and B are the divisors of C, such that with GCD of AB is 1, then AB divides C. See, A divides C, B divides C. AB divides C. When AB divides C, if GCD of AB is equal to 1, then only AB. So then you can do the product. And what? Here not C square. This is what? C. So we prove this one. So prove. So what? A divides C and B divides C. A divides C. That means what here? C is equal to AX, C is equal to BY, XY belongs to Z, XY belongs to Z. Right? Okay. Also we have just we applied the definition. A divides C, A divides. Just given that A divides C, A divides B divides C. Just this is our definition. Also what we have given, GCD of AB is equal to, we will apply that only. Okay. Also we have GCD of AB is equal to 1. Right. So that means what here? So I can write this is what? AQ1 plus BQ2. I can take any letters whatever I want. So this is 1. Okay. So Q1, Q2 belongs to them. This we must have to mention. What are your Q and Q2? Because QR and Q2 is not in the problem. Here X and Y are not in the problem. So that means you must have to mention what are your X and Y, what are your Q1 and Q2. You should mention this. Okay. So this is very important now to write XY belongs to that Q1, Q2. Now what here? 1 is equal to this. I can write here actually 1 is equal to. Okay. No. Okay. So here what? I should write 1 is equal to this. Okay. So this is not actually, we can, that was also correct, but I will write this. Okay. I will multiply by C now here. So C is equal to C, because what? I want to prove AB divides C. That means I want to prove C is equal to AB into some integer. This I want to prove. This is my aim, to prove that C is equal to AB times some integer. What do I have to prove? AB. So that means what? C is equal to, therefore I have multiplied by C here. So CAQ1 plus CBQ2. Now I will put the value of C now. I have the value of C is equal to X. I have value of C is equal to X. Which value I have to put where? So C here, C is here. Now A is there. A is there. I want to prove C is equal to AB. So I should have B here and I should have A here now. AB. So now C is equal to what I will put? The value of C is By now here and value of C is here what? Ax here. Okay. So I put the value of C here By AQ1 plus. Now I will put the value of C is equal to Ax here because I want AB together. So C is equal to AXBQ2. So what I will write? This is what? AB is there. Now see, product of the integer is commutative. You can shift anywhere. Okay. So that means what here? So I can take AB common here and this is what? YQ1. Again I can take AB. I have taken AB common here. So I can write this is what? AQ2. Now this X, Y, Q1, Q2. X, Y, Q1, Q2. So that means the linear combination is always integer. So all the integers, there is linear combination. This is what? Linear combination of this integer. So this is integer. That means what here? So C divides. So AB divides C. Because what? So C is equal to AB into some integer. So I write here YQ1 plus XQ2 belongs to Z. Yes? So this implies that AB divide C and that is our AB. Right? So very simple. We have applied the definition of the divisibility and we have applied the definition of the GCD. Can be expressed as a linear combination of this one. Your one is GCD, we have it, right? Only with the help of this we have proved the theorem. Only what we have applied our knowledge actually. Okay, where we have to put the proper value of C. Here we have put the proper value of C. If you put C is equal to X, then we are not true then, right? We will not be true. So that is what here we have. You have to put the proper value of C. Okay, because C have both the value Ax and By. Okay, I hope you understand this one. Okay, now we'll take the next one. Okay, so now we have seen this theorem, we have seen the definition of the GCD. I hope that you understand the definition of GCD and we have solved this through 3 examples on the GCD. So now this is enough. Okay, so we'll stop here. Thank you.